Hi everyone. Today I'm very glad to be here to introduce our work, the Hermes Attack, which is able to fully steal the DNN models without any accuracy loss. So nowadays, the deep neural networks have been widely used in a lot of areas, such as autonomous driving and privatization deployment. In those cases, the models are black box, but the users could basically access the inference platform, which increases the risk of the model leakage. As we all know that training a deep DNN model is very expensive. For instance, renting a GPU will cost around $4.5 per hour, and to get a high-quality DNN model, it will easily take around $400,000 or higher. Therefore, the importance of the model protection is self-evident. There have been a lot of work that in model extraction attack. However, to our best knowledge, all of them can only extract the partial of the DNN models, which means they cannot achieve the same accuracy as the original ones. Therefore, we propose the Hermes attack, which is a forced attack that can fully steal the DNN models. Now let's take a look at our stride models. We assume the host system and the GPU are already well protected. However, even under this scenario, the model is still not safe. The model information will be sent from CPU to GPU through PCIe bus, which makes the PCIe become a new attack surface to leak those confidential information. So our work is gonna prove that we can fully steal the DNN model from PCIe bus. There are several challenges need to be addressed during our attack. First of all, the most popular GPU runtime and driver, which is CUDA and NVIDIA GPU driver, is closed source. So we have to do some reverse engineering to review the PCIe traffic information. Secondly, there are a lot of noise packets in the PCIe traffic, and those packets are out of order. So we have to pre-process those traffic in order to get the correct order information. Lastly, some semantic, like layer types, are lost in the PCIe traffic. So we have to come up with solutions to recover those semantics. Before we dive into the attack detail, I'd like to first briefly describe some background knowledge. Here is a figure shows how GPU works. GPUs are worked under a command-driven working mode, like memory copy, counter launch are all controlled by the CPU using GPU commands, while those commands will include the data and the GPU code to pass to the GPU through the PCIe bus. And this figure shows an example of the PCIe packets. There are two types of PCIe packets. One is the read request packet, and which contains the targeting data read address. And another one is the data completion packet, which contains the requested data. Each request packet may have several corresponding completion packets, and they are connected through the same tag value. So for each GPU command, it will have the header and the data field. Each command is consist of several PCIe packets. Now let's take a look at our attack overview. While doing the inference, we will use the PCile Inteceptor to snoop the PCIe traffic sent from CPU to GPU. Then we will do the traffic processing to correct the PCIe packet order and extract the GPU commands from those packets, and then reconstruct the DNN model based on those extract commands. So for the PCIe Inteceptor, in our attack, we use the PCIe protocol and the ladder as the submitting device, which is marked in the green box. After intercept the PCIe traffic, the next step is traffic processing. Here is a screenshot shot from our intercept PCIe packets. If you take a look at the address, you will find that those packets are out of order. That's because the PCIe doesn't guarantee the arrival order of those completion packets. Now, let me show you how we solve those packets. Besides of the request packet and completion packet, there is another packet that generates from the interceptor, which is simply combine the address and data in text. So we first track the request packet, which contains the correct order information, and then we use the tag to locate its corresponding completion packets. Next, we can find the data packet through the packet ID and fill them with the correct order information, and then we can get all the data packets sorted. So after the traffic processing, we will need to extract the GPU command from the sorted packets. First, why do we need to extract the GPU commands. That's because there are a lot of noise packets, as we mentioned previously. The useful packets only take up around 2% overall. So we have to focus on those useful GPU commands. There are several different types of GPU commands, like initialization command, synchronization command, data movement command, and the kernel launch command. We only need the data movement command and the kernel launch command in our attack. They are noted as the D command and K command in the future slides. To extract those commands, we have to first identify the command header, so the offline training. So you may check out the detail of this part in our paper. So here is an example of the identified GPU command header. It contains the GPU address and the size of the data part in this command, and the command type. Because the GPU command consists of several PCIe packets, there could be some noise packet appear in between them. The noise packet could appear in both command header and command data. To address this issue, we can check the PCIe address consistency. In short, if the address of one packet is not consistent with its nearby packet, we will regard it as a noise packet and discard it. Now we have extracted all the GPU commands we need. The next step is reconstruct the DNN model from those commands. First one is the model architecture. The model architecture reconstruction is very challenging due to the semantic loss. To find out, we have to find out another representative of the layer types. Each layer consists of several GPU kernels, and each GPU kernel is represented as a key command in the PCIe traffic. But how to know what kernel it is? So we found that for each key command, it contains an address which pointed to the kernel binary. So we need to determine the layer types from the kernel binary. So comparing the kernel traces in the offline, we can determine the kernel type of this binary. Similarly, we can repeat the inference during offline and determine which kernels are used for each layer. Then we can put the kernel binary and the layer type pairs into the database. So during the online attack, we can directly get the layer type from the kernel binary using the database. But for non-sequential deep neural network like ResNet, we also need to recover the layer connection information. To make it, we build the data flow graph. So each vertex represents as a GPU kernel, and the input address and the output address are treated as the flow from and flow to. Then we substitute the vertices with the DNN layers, and the layer connection could be recovered. So the next one is to the hyperparameters. Some of the hyperparameters are included in the key command, such as the kernel size, the stress. We found out the offset of this hyperparameter from offline training and put them into the database. During the online attack, we can directly use the offset to obtain those hyperparameters. Another kind of hyperparameter, like activation function, we cannot directly get from the key command. In this case, we can infer the activation function type by checking if the corresponding GPU kernel is appeared after this key command. So the last one is the parameters. Parameters usually including the weights and bears. Since the data could be moved into the GPU, we have to track those data movement commands. The key command could provide us the destination address of those parameters, and by tracking the data move command, we can find the original address. Then means we can get those data we want. So then we got the evaluation. We have evaluated our attack on 3 GPU platforms, which represent 3 different generations. And we have verified our attack on 3 DNN models, which are MINIST, ResNet, and VGG. Let's first take a look at the model architecture difference. There are several differences. There are 2 differences here. The first one is we treat all the activation function as single layers. There is no semantic difference compared to the original one. So it won't make any influence on the inference. Another difference is that the generated model doesn't contain the dropout layer. That's because the dropout layer is only used in the training phase. So again, it won't make any influence on the inference. The REST and VGG are very similar to the MINIST, except those two minor differences mentioned previously. All the remaining are exactly the same. Now let's see the performance. For the accuracy, all the generated models have exactly the same accuracy with the original ones. For the inference speed, they are very similar, and the difference is considered as some normal fluctuation. We also measure the extraction efficiency. The results show that our attack could be completed just within several minutes. So the efficiency could be varied upon the attacking platform and the complexity of the victim model. To sum up, we are the first attack that could fully steal the DNN models without accuracy loss. And the attack is wide on different platforms and the different models. And that's the end of my presentation today. Thank you so much for your patient attention.